Hello, and welcome to CHEM111 Flex Lab, Chemical Equilibrium Part 1, Constructing a Calibration Curve. In this experiment, which is a two-part experiment, we are going to study equilibrium and how outside forces affect chemical equilibrium. In Part 1, we're going to utilize absorbance and Beer's law, also known as Beer-Lambert law, to construct a calibration curve. So we're going to be utilizing stoichiometry. Stoichiometry measures that color intensity. And that color intensity is going to be directly related to the concentration. That is demonstrated by the Beer-Lambert law, where the absorbance is proportional to both the concentration of the solution as well as the path length of our little cuvette. We did some absorbance studies back in Chem 110. The calibration curve is going to confirm Beer's law, and by doing so, we should get a nice straight line plot with a zero intercept. After we get this calibration curve in Part 2, we can utilize it to determine concentrations of unknowns by looking at their absorbance. We're going to be using varying concentrations of iron thiocyanate, which absorbs at 447 nanometers in order to construct our curve.
So we've got a couple of experiments where we specifically need to be worried about our glove protocols. And those experiments are the solution concentration, the titration, standardization, and the titration for the vinegar concentration. So when we talk about those experiments, it's absolutely necessary that we wear gloves for the entire experiments. For the other experiments, gloves are recommended. They're not necessarily necessary. It's never that we don't want you to wear them, but you don't have to wear them for the other experiments. For these, it's necessary. So I want to show you how to properly put on a pair of gloves, how to take them off, and then talk about what are proper protocols for using those gloves in those experiments. So let's talk about how we put those gloves on. So we're going to take gloves out of this container. Here's one, here's two. I'm going to set those down. We're going to make sure that we put them on appropriately. So we want to make sure that we get our thumbs into the thumb spots on our gloves. So that's one. I want to get that over my watch because I want to make sure I don't kill my watch while I'm wearing it. And then have my second one, if I can get this thing sorted out because they're all shoved in there, not necessarily easy to put on. Some people take their rings off before they do this. It depends on how big your rings are. I have ones that are tiny so I don't break through my gloves. That was a decision we made. But these are how I put them on. Putting them on is the easy part. Okay? Taking them off is not the easy part. When I'm in the lab and I'm working with these gloves, everything is fine. If I have to leave the lab for whatever reason, I need to go to the bathroom, I need to take a phone call, I need to eat something, I need to do something outside of the lab, including taking a drink, then I need to take these gloves off. So if I'm going to take these gloves off, I can take the first one off fairly easily, right? Fairly simple. But when I go to take the second one off, I want to hook my fingers inside of it, grab a hold of the inside, and then pull it off like that so that I'm holding the inside when I'm dealing with it, not the contaminated outside part of the glove. And then I take those off. I'm then going to wash my hands to make sure that I get anything off of my hands that shouldn't be there, because sometimes we accidentally get chemicals inside, okay? And then I'm going to go do whatever I need to do. When I come back to the lab, I'm going to go to the front bench. I'm going to wash my hands again, just because I'm paranoid. And then I'm going to put on another pair of gloves. And I'll do that before I handle anything in the normal part of the lab. Okay, because chemicals can be just about anywhere. So we want to make sure that we're dealing with clean hands before we put them back into those gloves. Now, things that we need to make sure that we're dealing with when we talk about these experiments. We put those gloves on before we handle anything, because you may not be the first lab for that week. So the things that we're dealing with may not be as clean as we want them to be. So we want to make sure that we're dealing with, everything in gloves. So make sure we've got those dealt with the gloves on. Anything that we deal with in the lab needs to be done that way. Anytime anybody is working with anything, doesn't matter if it's chemical or not, for those labs, we need to be wearing those gloves. Okay? So I think that's everything I need to talk about with the gloves. So thanks, guys. I appreciate it. So in this experiment, we're going to be working with the same experimental setup that we used in 110 for the Powerade labs. So this is just to collect spectrophotometry data. Now we're doing this because, as we know now, the Beer-Lambert law describes the relationship between absorbance and concentration. However, we want to make the math a little more complicated for you. Some of these things only record in percent transmittance. So we have set this up so that you're recording in transmittance, which is this percentage right here. We're going to be doing this at approximately 447 nanometers. You'll see it's 446.7. That's the closest we can get. And for this first part, we're going to be generating our calibration curve. What we've created is this red thiocyanate complex with iron. And this we will make in several different concentrations. So there'll be 5 different concentrations that you will make. We need to take the percent transmittance of those solutions. So what we'll do is once we've created one of those solutions, we'll pick this up. We'll put this in here. We need to make sure this is approximately 3/4 of the way full. And then we'll drop this into the spectrophotometer so that we can measure that percent transmittance. And you'll see that goes down to 22.7 for this particular solution. There'll be a number of different concentrations that you'll measure for this. After the lab is over, you'll use that to generate a calibration curve, which will be able to tell you, based on the percent transmittance, what that concentration is. So that's the first part of this lab. Now, a couple of notations for you about how to handle the chemicals that you're working with. You'll notice that I'm wearing my lab coat today. I don't normally wear my lab coat, but these things stain very badly. We're also working with nitric acid at a higher concentration than what we've normally used, so you need to make sure that you're extremely careful with it. We need to wear gloves for all of this. You need to make sure that you're as covered as you can possibly be. We need to make sure that if you have any spills with the nitric acid, you let someone know immediately with that. And you're going to have to add that acid to the potassium thiocyanate and the iron complex. So you mix the iron and the potassium thiocyanate, and then you will add the acid to it. So do like you otter, add acid to water, and the acid goes last. It will generate a lot of heat, so you're going to need to make those solutions and let them cool before you take these measurements. So it will take a little bit of time, okay? But that's all you need to do for part 1.
So we're going to be talking about data collection and potential errors, and we're going to be talking about this in general. It's going to apply to all of our labs, so this is going to be the same conversation you're going to hear for every lab, but I need you to pay attention to the same things and learn to apply them for each of the experiments. When we talk about data collection, there are certain pieces of data that you're going to be asked to collect. Depending on which lab it is, that's going to determine which pieces of data you're going to be asked to collect. It's not going to be the same every time. Sometimes we're going to ask you to collect one piece of data one time. And that's because we're interested in making one observation about that piece of data. Okay, so it's just one piece of information that we're going to collect that one time. That's typically a qualitative observation that we're looking to make, so just information without a lot of specifics about it. Okay. On the other hand, we may want to take that piece of data twice to see if it's reproducible. Okay, so typically if we're going to do that, it's going to be a numeric piece of data, and we're going to be very specific about how we take that piece of information. Now, we either take it once, twice, or many times. Now that many times is going to depend on exactly what we're doing and how we're doing it. In this class, we will limit that to 3. It never goes beyond the 3. But out in the real world, that many times could be 5, 10, 20, 50. Could be any of those things. The reason for that is because it becomes statistically significant. So if you've taken Math 120 and you know about statistics, you understand that we need multiple data points to be able to determine if those data points are statistically significant. So we need to know if that's really true for the data points that we've taken. We can't get rid of them if they look wonky, if we don't know what wonky actually looks like. So we need to take multiple points to be able to see if that data is real or not. Okay. We typically don't do that in this class until we get into the later labs. So the titration labs, the first times that we start looking at that number of data points. We do start taking more data points as we go forward. So in the beginning, we take 1 data point. Later on, we take 2 data points. At the very end, we start taking 3. If you have the privilege of taking CHEM111, then you get to take many data points the whole time. So look forward to that. Okay. those are important things for us to be paying attention to. The other thing that you need to be thinking about is what kind of data are you taking? Because the kind of data that you're taking determines how precise you need to be with the information that you're collecting. The instrument that you're using typically gives you an indication of what kind of precision you need for that particular measurement. When we talk about the electronic balance, there's only a certain number of numbers on that balance that we can look at. There's no way we can estimate beyond those numbers. So that's what we're going to record. But when we talk about something that's a volumetric piece of equipment, we can usually estimate beyond the last thing that we can look at. So on a graduated cylinder, we can estimate beyond the last measurement that's there, in between those last measurements that are there, and so we can estimate that last data point. When we talk about something like a volumetric pipette, which is one of these guys, for this, there's a finite measurement that's here, and we can't estimate beyond that. We know exactly what that is, and so if this is a 1 milliliter pipette, we know that this is 1.00 milliliters. That's the precision that we know for that particular instrument. So the type of instrument that we're dealing with will tell us what kind of precision we have for that number. It's important that you pay attention to that and record exactly what it is. You will see that when we're in ALEKS, it will be very specific about that. So if you don't have the right number of numbers, that's going to be a problem. We need to know how many numbers it is, because that determines our number of significant digits, which then determines how significant those calculations are going to be, which then determines how significant our answers are going to be. So this becomes something that we have to carry through all of the calculations that we do. That's important. Okay. So that's all of the data that we collect, how we have to be careful with the numbers that we're collecting, and the type of information that we're looking at. Now, every piece of data that I collect has to have a unit. If I see numbers that don't have units, most of us will flip out about that. Okay? Units have to be there. Is it a gram? Is it a milliliter? Is it a kilogram? Those are important. We have many times that scientific numbers are recorded in the US and then sent to the UK, and assumptions are made about what units those were, and then an assumption is made when they go to the UK, they do something with it, they make some kind of conversion about it because an assumption was made, and then they do some conversion to it before they send it back to the US, and then the US gets those numbers back, still without units, they do some other conversion to it, and then some $2 billion mistake happens. Welcome to the Hubble telescope. Okay? These things happen, and this is a really big deal. If you've made it one of those, been part of one of those calculations where a $2 billion mistake has happened, that's the kind of thing that gets you fired. So a simple putting the unit at the top of the column of numbers is a really big deal. So recording your units at the top of a column or with that number becomes very important. It's a habit you should be building now. So the numbers that you're recording should have those units. Okay? So make sure you're doing that with your lab materials. Make sure that you're doing that on your tests. If they're not on your tests, that's a problem too. Okay? So those are the data that we're collecting, the number of significant figures that we have to have, the type of data that we're collecting, i.e. the units that they are. And then we need to talk about potential errors. Everything that I measure has a potential error that can go with it. So if I'm using one of these volumetric pipettes and I'm not particularly skilled at doing so, there are errors in the way that I may be doing that. It may be too high, it may be too low. There are inherent errors in that particular measurement. If I'm particularly precise in how I do it, then I don't have to worry about those errors. But if I'm not precise, I need to be honest about that. Okay? That's something that I need to record when I'm doing my data collection. So if I say to myself, okay, I wasn't paying that much attention, and it might have slipped down below where it should have been, I need to write that down because that's a potential error. That can affect a lot of the things that happen after that. Because if my volume was too small, then the concentration that I'm going to end up with is going to be too high because my mass is going to be in a smaller volume, which means a larger concentration, which therefore is going to affect all of the information that I'm collecting off of that concentration. these are implications that I have to be able to think about. Okay, so anything that you do may have implications down the road. So you have to think about what you did. If you took a mass on the balance, we always talk about it doesn't need to be exact. It absolutely does not. You do not need to spend a ton of time getting the exact number that we've asked you to get. Don't. It's a waste of time. But you need to record exactly what it was, okay? And if you do what some students do, and you don't bring your paperwork with you and write down that number when you're at the balance, and you walk away and then record the wrong number, then that's a problem, because you don't know if it's too high or too low. So one of the things that you need to be aware of is that when you go to that balance, you should be taking your paperwork with you to record that number at the balance. One of the things that I do to my students is if I see them walking to the balance without that piece of paperwork, is I will follow them from the balance back to their bench, and I will sing things like 8675309 so that they forget whatever the number is. Or if I see them writing it on a small piece of paper, then I will take that paper and burn it, because that's who I am. These are things that you really should not be doing. They're bad habits that you cannot afford. Okay, violations like that in terms of, federal regulations are $10,000 per incident per day violations. That's expensive. Okay, your company doesn't want that, and if you're responsible for it, that's something you can get fired for. Okay, so those are important things to think about. All of these errors have places where they can cause problems. We want you to think about the errors that you may have. When we ask you about errors, an answer that is completely unacceptable is human error. What the heck does that mean? What errors did you make? What could you have done? I may have made mistakes in measuring. Okay, what measurements could I have made mistakes with? Was I imprecisely reading my volumes because I was too lazy to pick up my things so that I was reading the meniscus correctly? If that's the case, then maybe we should talk about making sure that we're having that meniscus at eye level so that we're seeing it appropriately. Okay, are there things that we could do differently? Now, just because you're not aware of that at the beginning doesn't mean you can't improve on it as you go forward. That's part of the reason that we look at this after we do an experiment, because we're learning to look at how we did that experiment critically to see how we could do it better the next time. We need to be able to do that for ourselves and for the next person who does this lab, so that we can say, hey, try this instead, do this differently, so that maybe you can do it better next time. That's an important part of our ability to be scientists, is to be critical about what we did. It doesn't mean you're wrong, it doesn't mean you do it badly, it just means that you have to be honest about what was done. Okay? So be willing to look at what you did and what are real places that you could have made a mistake. Okay? Those are important things. When we transfer solids, often we lose some of that material, so make sure that you've noted it places where that may have happened, especially if you actually see it during the experiment. You should write that down. You should talk about the fact that that happened. So any of those errors should be noted in your paperwork, and it should be something that you talk about in the paperwork for your experiment. Okay? So those are the potential errors that you may see. Now, those are all going to be based on the particular experiment that you're doing. I'm not going to specify for each lab where those things may be, because it's your job to figure out where they might exist. Okay? This is a gentle reminder that you need to be looking at every experiment to see what kinds of things was I recording, what kind of mistakes could I have made, what things do I need to be paying attention to. So that's my spiel about data collection, units, errors that you might have made, and how those errors could implicate the data that you're looking at. So hopefully that will help you with some of those things and get you on the right track. Thanks, guys.